So we're going to look at an energy diagram, total energy line, and we're going to have a curve. So just a random curve, and we'll do this one in red like we did before. Okay, so now there's 2 points of interest on this graph. Now those points are where the graph turns. So we got 2 of them here. Okay? So they're known as turning points or equilibrium points. Now, what does that mean? So there's 2 different kinds. One's like a hill, and one's like a little valley, if you will. So let's name. We'll label those. We'll say point one and or point A and point B. And so let's look at point A. So point A is known as an unstable equilibrium point. Okay. Now, one of the easiest ways that I like to think of what makes it unstable and stable, or how to know it's unstable or stable, is imagine that that was like a hill that you were to put a marble on. Okay. Now there exists some point on that hill where the marble would be at rest. It would be in equilibrium. But if I nudge it just a little bit in any direction, it's going to immediately roll off the other side and will never come back. Okay. Or at least there will be some additional work required to bring it back. Okay. So I look at the unstable equilibrium as a point where things can come to rest, but then they'll start to fall again. So like that would be a ball being thrown up in the air. It hits an equilibrium point when it's at the max height, but then it starts to fall back down. Okay, the next is a stable equilibrium point at B. And if we use the marble analogy again, there exists a point below, on the bottom of that valley, where the marble would be at rest. Now, if you were to nudge it in any direction with a force, all that marble is going to do is roll slightly up one side, and then it'll come back down. And it might go back and forth a little bit until eventually it comes back to rest at the bottom of that bowl, if you will. So I call that's stable equilibrium, because even if I nudge it, it'll eventually return to that point. All right, now an example of stable equilibrium would be a spring. Okay, no matter how much I compress or pull on that spring to either push it in or stretch it out, it will always try to return back to that equilibrium. Okay? So when the thing wants to return to equilibrium, it's stable. When it's in equilibrium, but at any moment it could move away from equilibrium, then it's considered unstable. Now let's remember what equilibrium actually means. So recall from before that when something was in equilibrium, that meant that all the net force acting on that object was 0. This means at points A and B, the net force is 0. Okay, so for calc students, what part of the graph at points A and B is 0? And for the non-calc students, you could answer this as well. What property of the graph at points A and B is also 0? Okay, so if you can answer that question, the answer is slope. Right? At point A and B, the slope of that curve is 0. So that's an important connection. That means that we have a connection right now to argue that the force F that is applied to an object can be read on an energy diagram as the slope of that diagram. Okay, so let's make a guess to this. Let's say, so we'll make a hypothesis here that force F is the slope of the energy diagram. All right, so then let's try to make a proof for this. All right, so in order to prove this point, let's think back to work. So remember, we know that from the work energy theorem, work causes a negative change in potential energy. And remember, it's negative change because whatever we took from potential goes into kinetic. Okay, and recall that work was also force times displacement. Now if I solve this for F, I get the negative change in potential energy divided by x. Well, the displacement. But if you look at the graph, the y-axis is potential energy U, and on the top we've got change in U. On the x-axis, it's position x, and in the denominator here we have change in x. So on the graph, this really is connected to a rise over run. So in fact, we were correct. Force is the slope. And if we were to look at tiny infinitesimal changes in the curve, so over very tiny displacements, then the force is simply the negative derivative of the potential energy function. Okay? And you could try this with the two energies we already have. If you do the negative derivative of potential energy, mgh, you get negative mg, gravity. If you do the negative derivative of elastic energy, you get negative kx, which is Hooke's law. So it turns out that yes, from our hypothesis, force is the negative slope of a potential energy curve. Okay, so it's important to understand the negative part. So if the graph is going upwards, for example, then that means it has a positive slope, but since force is the negative slope, that means you're doing a negative force on it. Again, think of gravity. If I take an object and throw it in the air, it's losing potential energy. Oh, sorry, take that back. I throw the ball up in the air, it's losing kinetic energy because gravity is slowing it down. Gravity is a negative force, and that negative force is causing the potential energy to increase. Then when you come down on the other side of that curve, well, what happens? You're gaining potential energy because the slope, which is now a negative slope on a downward curve, means that the force is negative of a negative, so the force becomes positive. And if the force does positive work, kinetic energy will increase. Okay. All right, so connection there on the graph that force is actually the negative slope of an energy diagram, that force is actually the negative derivative of potential energy. An energy diagram shows the total mechanical energy, the potential energy, and the kinetic energy for any given position. And then we also had two equilibrium points, one of stable equilibrium, one of unstable equilibrium. Remember, unstable is like being at the top of the hill. You can roll off any side with just the slightest push. And stable equilibrium means you're at the bottom of that valley where any push, you won't get out of that equilibrium point easy. You need to do a lot of work to get out of it. All right, so that's energy diagrams and a little bit of calculus involved with energy.